In your exams, it might have the possibility to ask a question like find the average molecular energy. Means the average energy of a molecule inside infinite number of molecules of an ideal gas. So you can see that for finding here this symbol corresponds to average molecular energy. You can see that for finding this average molecular energy, you actually need this N of ED, and this N of ED is actually the number of molecules lies in between the energy range E to E plus D. So our first target is to find this N of ED. For that, let me first draw a momentum space. From classical mechanics, we already know that each momentum corresponds to a state. So, this is not a circle. This is actually the spheres in three-dimensional space. So, this P corresponds to a sphere of radius P, and this P plus dP corresponds to a sphere of radius P plus dP. So, the number of states lies in between this momentum range P2 P plus dP is directly proportional to the volume of this shaded region. So I can write you can simply see that the volume of this shaded region is 4 pi p square dP. That is, this 4 pi p square is actually the area of this sphere. So times dP gives the this area of this volume, this shaded volume. So the volume of this shaded region is 4 pi p square dP. The number of states, momentum states lies in between this momentum range is g of p dP, and it is actually proportional to this volume 4 pi p square dP. So in general, I can write the number of momentum states g of p dP as is equal to a p square dP, where a is a constant. We will find it later. And actually, this g of p dP is equal to this g of E dE, because each momentum magnitude p corresponds to a single energy E. Because each momentum p corresponds to a kinetic energy p square by 2, which is equal to the kinetic energy or the energy here. So simply each momentum state is corresponds to a single energy state E. So we can write g of p dP is equal to, so we can write this d of p dP is equal to this d of E dE. We know that p square over 2m is equal to energy. So from this equation you can simply write this equation, that is p is equal to root of 2me, and this implies dP is equal to m over root 2me times dE, because this taking derivative on both sides of this equation gives 2p dP over 2m is equal to dE. And let me cancel this 2 from both sides. Let me put p is equal to root 2me here. That gives root 2me over m times dp is equal to dE. So from this equation I can write this gives dP is equal to, so we get dP is equal to m over root 2me times dE. So you can see that here dP is equal to m over root 2me times dE. So on substituting this value of P and this value of dP in this equation for g of E dE gives a times 2me times m over root 2me dE. From this equation you can simply see that this E and you can simply see that this E and this E cancels and gives root E in the numerator, and also this m gives m square in the numerator. So m square upon root m gives, which is m square upon root 2m is equal to m to the power 2 minus 1 by 2, that is equal to m to the power 3 over 2. So you can see that this m to the power 3 over 2 in the numerator, this m to the power 3 over 2 in the numerator, and also this 2 and this root 2 give root 2 in the numerator. So in total you get this a root 2 m to the power 3 by 2 root ed. Our task is actually find this n of ed. So we already know from Maxwell-Boltzmann distribution function this n of ed is equal to f of e g of e d. There's actually an equal sign here. I missed it. And this f of e is the Maxwell-Boltzmann distribution function. We already derived this Maxwell-Boltzmann distribution function in our classroom lectures. So we know that this distribution function f of e is e to the power minus e over kbt. Kb is the Boltzmann constant, and g of e d is the number of energy states lies in the range dE, or we can say that it's actually the density of states in some sense. So substituting this g of e dE here, substituting this g of e dE here gives n of e d is equal to a constant c times root e to the power minus e over kbt d. This is actually epsilon. I accidentally call it e. So remember that this is epsilon denotes the energy in our case. You can see that this c here represents c is equal to a root 2 m to the power 3 by 2, and the remaining root e is here, and the e to the power epsilon over kbt is here. So now we have n of d in our hand. Our task now is to find constant c this constant c. We know that the total number of molecules is constant, and it can be found by integrating over all energy states. So the total number of molecules is n is equal to integral running from 0 to infinity n of e dE. So that is actually c integral 0 to infinity root e to the power epsilon over kbt dE from this equation. So to integrate this, you actually need a trick of gamma functions. Let me explain this trick briefly for you. The gamma function can be drawn as and this is the value of n. So the gamma function in the y-axis as gamma n. Remember that this is the symbol for gamma of n, and here the graph is like something like this. And also we have another formula for gamma function as gamma n is equal to integral 0 to infinity x to the power n minus 1 e to the power minus x dx. This is the thing that we apply in our calculations. And also there are some other properties of gamma functions, as we can write the gamma function as gamma n is equal to n minus 1 factorial. And you know that this n minus 1 factorial is equal to n minus 1 times n minus 2 factorial, and actually this n minus 2 factorial is equal to n minus 1 gamma n minus 1. Why? Because gamma n minus 1 is equal to n minus 1 using this formula. This gamma n minus 1 is equal to n minus 1 minus 1 factorial, that is equal to n minus 2 factorial, and this n minus 2 factorial is here. So we just change it as gamma n minus 1. And also we have another formula, that is gamma 1 by 2 is equal to root pi. We get this result from this integral. So if you integrate the expression integral 0 to infinity x to the power 1 by 2 minus 1 e to the power minus x dx, which is equal to integral 0 to infinity x to the power minus 1 by 2 e to the power minus x dx. You will get this as root pi. If you integrate it, you can see that. And this root pi is equal to this gamma 1 by 2. This gamma 1 by 2 is here. So gamma 1 by 2 is equal to root pi. Our task is to find integral 0 to infinity x to the power 1 by 2 e to the power minus ax dx. So to use the trick of gamma function, our task is to convert this formula to this form. If we are able to convert this formula to this form, we can use simply this trick to solve this integral expression. So for that, let me first multiply this x with an a here, a x 1 by 2, ax whole to the power 1 by 2, e to the power minus ax, and also I just put a here. It's a constant, so we don't have to mind it. But if we put these constants in this expression is little bit different than this expression. So to make this expression equal to this expression, we actually multiply this expression with this a to the power 1 by 2 in the numerator. So we multiply 1 by a to the power 1 by 2, and also you can see that this a comes here. So to avoid the contribution of this a, we need to multiply 1 by a. So if you multiply this expression with the factor a to the power 3 by 2, you will get this expression. So these two expressions are equal. So we are now able to apply the trick of this gamma function, because this is actually in the form, you can simply see that this is actually in the form 0 to infinity. This ax can be let me put this can be some y to the power 1 by 2, e to the power ax is y, and dx is dy, and also we have a factor 1 by a to the power 3 over 2. So these two expressions are same, 0 to infinity y over 1 by 2 e to the power minus y dy, and that is same as x to the power n minus 1 e to the power minus x dx. So we can write this 1 by 2 as integral 0 to infinity y to the power 3 by 2 minus 1 e to the power minus y dy times 1 over a to the power 3 by 2. And also this is actually equal to, we can apply the result here. So this is equal to 1 over a to the power 3 by 2 gamma 3 by 2. Why? Because this is gamma n. This expression, you can see that this is gamma n. So this is gamma 3 by 2. So gamma 3 by 2 can be written as 1 over a to the power 3 by 2. Gamma 3 by 2 can be written as 1 by 2 gamma 1 by 2 using this expression, using gamma n is equal to n minus 1 gamma n minus 1. So gamma n is equal to n minus 1 gamma n minus 1, that is we have gamma n is equal to n minus 1 gamma n minus 1. So gamma 3 by 2 is 1 by 2, gamma 3 by 2 is 1 by 2 gamma 1 by 2. So this is equal to 1 by a to the power 3 by 2, 1 by 2, and gamma 1 by 2 is root pi. So now we have this integral as integral 0 to infinity x to the power 1 by 2 e to the power minus ax dx as 1 by 2 a to the power 3 by 2 root pi. We can split this as 1 over 2 a root of pi by a, because root a times a, that is a to the power 1 by 2 times a is equal to a to the power 3 by 2. So using this trick of gamma functions, we have integral 0 to infinity root x e to the power minus ax dx is equal to 1 over 2a root of pi by a. And you can see that a in this integral is actually 1 over kbt. So simply you can see that a is equal to, from this integral, a is equal to 1 over kbt. So substituting that value for this a, you get you from this equation you can see that this a and this a together gives 1 by a to the power 3 over 2 in the denominator, and a 2 here and a pi here. So that integral becomes c over 2 kbt to the power 3 by 2 root pi. This is root pi, this is root pi, and this 2 is here, and this a to the power 3 by 2, here it is kbt, it is in the numerator, because a is equal to 1 by kbt and this kbt is in the denominator. So in total this kbt comes in the numerator. So from this equation, you can simply reverse this equation and find c as 2 pi n over pi kbt raised to 3 by 2. What we actually did is we just take this root pi inside this kbt to the power 3 by 2. So I just take kbt pi over 3 by 2 over pi. So in total these two pi's will give, you can see that this pi, if this pi comes in the numerator, you get pi to the power 3 by 2 minus 1. So this in total give pi to the power 1 by 2, that is root pi. So I can, for our convenience, we can take this pi inside this kbt and we can write this c as 2 pi n over kbt to the power 3 by 2. So if we substitute this c, in this equation, we will get n of e dE as 2 pi n over pi kBt whole to the power 3 by 2 root e to the power minus e over kBt dE. So now we have n of e dE. Maybe this also can be asked in your exams. Now we have this n of e dE. Now our target is to find the average molecular energy. I think you already know this type of averages. I think you already know this expression. So if you don't know, let me interpret it for you. Suppose n1, suppose you have n1 number of particles have energy E1 and n2 number of particles have energy E2 and n3 number of particles have energy E3. So how can we find the average energy? We can find the average energy by summing the total energy. This is actually the total energy. N1 number of particles have E1 energy, N2 number of particles have E2 energy, and N3 number of particles have E3 energy. So this is actually the total energy. Total energy divided by total number of particles. That is N1 plus N2 plus N3. That is actually N1 plus N2 plus N3 is actually N. So this gives the average energy. And here we have continuous states, means not like this discrete. We don't have this type of discreteness, that is E1 E2 E3. We don't have it. So this numerator represents this total energy. This numerator represents this total energy, and this denominator is this. So this is the interpretation for this equation. So on substituting this n of e d here, you will get this equation. Just change in the power of this e, because this e and this root e together give e epsilon to the power 3 by 2, and this exponential factor is still there, and this 2 pi and there this n is cancelled by this n, so that n doesn't appear here. So 2 pi by over pi kBt whole to the power 3 by 2 is here. This integral is actually done by the trick of gamma functions. You can see it here. Let me explain this trick a little briefly for you. Now we have to integrate integral 0 to infinity x to the power 3 by 2 e to the power minus ax dx. Let me make this expression as ax to the power 3 by 2 e to the power minus ax dx and a factor. What is the factor here? And a to the power 3 by 2 we add in the numerator, so we multiply in the numerator, so we have an 8 to the power 3 by and 8 to the power 3 by 2 in the denominator due to this 8 to the power 3 by 2 in the numerator, and also we have an a in the denominator, sorry, in the numerator, this a. So we need to avoid the contribution of this a by multiplying this expression with 1 by a. So I put this a here. So these two expressions are now equal, and you can see that this expression is actually you can write this 3 by 2 as 5 by 2 minus 1, that is 5 by 2 minus 1 is 3 by 2. So you can simply see that this expression is gamma 5 by 2, because this is actually equivalent to integral 0 to infinity x to the power 5 by 2 minus 1 e to the power minus x dx. We just change the integration variable from x to x. So that gives gamma 5 by 2 times the factor 1 over a to the power 3 by 2 times a. So gamma 5 by 2 is, we know that gamma n is n minus 1 gamma n minus 1. So we use it. This gamma 5 by 2 can be written as 3 by 2 gamma 3 by 2, and this gamma 3 by 2 can be written as this 3 by 2 here, and this gamma 3 by 2 is 1 by 2 gamma 1 by 2, and this gamma 1 by 2 is root pi, and this 1 by 2 here, and this 3 by 2 here. So 3 by 2 times 1 by 2 times root pi, so that is 3 by 4 root pi. So I put that here. We get 3 by 2 root pi times 1 over a to the power 3 by 2 times a. I can write this a to the power 3 by 2 to a as root a square, because root a is equal to a to the power 1 by 2 and a square, that is actually a to the power 1 by 2 plus 2, that is, which is equal to a to the power 1 plus 4 over 2, which is equal to a to the power 5 by 2. So I can write this expression as 3 by 2 root pi over I can write this as 3 by 2 1 over a square times pi by a, as which is equal to integral 0 to infinity x to the power 3 by 2 e to the power minus ax dx. Not 3 by 2, this is actually 3 by 4, because 3 by 4 here, because this 3 by 4 is here, so we have actually 3 by 4 here. So now we have, using this trick of gamma functions, we have integral 0 to infinity x to the power 3 by 2 e to the power minus ax dx is equal to 3 over 4 a square root of pi by a. And in our expression we already know that this a is equal to 1 over kbt. So if you substitute that kbt in this expression, you will get this e as this 2 pi over pi kbt 3 by 2 is still here, and this 3 by 4 is here, and this a square as kbt square, because a is equal to 1 by kbt. So 1 by a square is equal to, so 1 by a square is equal to kBt whole square. So, and this root pi by a, uh, root pi by a becomes root pi by a becomes root pi a is 1 by kBt. So 1 by kBt here gives kBt in the numerator. So you can see that here. And this pi and this root pi together gives pi over 3 by 2 here, pi over 3 by 2 here, and these 2 and this gives 2 into 3, and these 4 in the denominator, and this kBt 1 by 2 kBt whole square, that together gives 1 by 2 plus 2, that is 1 by 2 plus 2 is 5 over 2. So you get kBt to the power 5 over 2 here, and also this pi to the power 3 by 2, this pi to the power 3 by 2, and also this kBt to the power 3 by 2. So you can simply cancel this pi 3 by 2, this pi 3 by 2, this 2 and this 4, that gives this 2, and also this kBt to the power 5 by 2 and kBt to the power 3 by 2, that together gives kBt, because 5 by 2 minus 3 by 2 is equal to 1. So we get the average molecular energy as 3 by 2 kBt. So we get the average molecular energy as 3 by 2 kBt.